All right, good morning, folks. We're going to continue with our chemical equilibrium calculations. In this topic, calculations involving chemical equilibrium are discussed. We're going to look at many ways that you can be asked to solve problems on that chemical equilibrium. So let's move on. Let's move on to the first example.
Consider the following reaction at 350 degrees C. Assume the equilibrium concentration of Cl2 and CoCl2 are the same at 350 degrees C. Calculate the equilibrium concentration of CO. First, write the expression for the equilibrium constant. K sub C is equal to the concentration of CoCl2 divided by the concentration of CO times the...
Now remember, when you do that, the product over concentration of the reactant is what we are doing here. And your Kc, equilibrium constant, equals to that expression.
Since the equilibrium concentration of CoCl2 and Cl2 are the same, they cancel out from the expression. Therefore, 1 divided by the concentration of CO is equal to 2.4 times 10 to the power 3.
All right, remember that it was given right here in the question that the concentration of Cl2 and CoCl2 are the same. That was why these two cancel out. So what you have is 1 over CO. Okay?
Therefore, the concentration of CO is equal to 1 divided by 2.4 times 10 to the power 3.
All right, any question on this? I guess this is straightforward. All right, let's move on. Remember, you can watch the video again so that you can take down your notes.
The concentration of CO is equal to 4.2 times 10 to the negative 4 molar. Example, consider the following reaction at 300 degrees C. Assume the equilibrium partial pressures of NH3 and N2 to be 0.030 atmospheres and 2.4 atmospheres respectively. Calculate the equilibrium partial pressure of H2 at 300 degrees C. Write the expression for the equilibrium constant.
All right, go ahead and write the equilibrium expression for that, which is straightforward. Now remember that Kp is equilibrium pressure expression, not concentration at this time. We're looking at pressure because they are all gases, and the question is trying to find out the equilibrium concentration for the pressure, or equilibrium pressure of the expression rather. So in this case, you know, this is your product, and this is a bracket which is allowed for pressure. Since you're not looking for concentration, you're just looking for pressure expression. All right, so this is your product and this is your reactant. The two reactants comes to the bottom. Okay. All right, that will give you this expression. So the Kp in this question would be this. All right. Your pressure for ammonia, if you look at the question, is assuming the equilibrium partial pressure of ammonia and nitrogen to be this and this, respectively. So this will be for ammonia. So this goes right here. And then this goes right here. All right. And then you just have to solve this problem. After you have plugged in the values, you look for the solution. All right, that should give you
The partial pressure of
205.
H2 is equal to
When you all right, in order to get the partial pressure of hydrogen, because remember, partial pressure of hydrogen cube equals to 25. So you find the cube root of 25. That should give you something like 2.9 or so, thereabouts. $2.9. Any question on this? You can pause the video to check it again. Make sure you use your calculator to check the answers.
In this section, calculations involving chemical equilibrium are discussed. Example, a 5.00 liter flask contains 7.00 moles HI, 8.20 moles H2, and 0.60 moles I2 in equilibrium at a particular temperature. Calculate K sub C at this temperature for the reaction. First, write the expression for the equilibrium constant. K sub C is equal to the concentration of HI to the second power divided by the concentration of H2 times the concentration of I2. Remember, brackets are used to express molarity M, and the units of M are moles per liter. The volume of the flask is 5.00 liters. Thus,
so in this case, since you are given moles, you are given volumes in liters. To get your molarity, remember, is moles, number of moles, divided by volume in liters. All right, that is what you're going to use to get your molarity, which is also called the concentration in this situation. All right, this is
K sub C is equal to 9.96.
All right, I need to flash back a little bit so that you understand what is going on here. Now, the concentration of HI is found to be 7 moles over 5 liters, which is the volume of the flask. For H2, it's going to be 8.2 moles over 5 liters, which is the volume of the flask in liters. And I2 is 0.60 over 5 liters of volume, which is the volume of the flask. So now, putting all this together, substitute into these values, to HI over H2 and I2. You get that.
K sub C is equal to 9.96. Note, in this problem, you could have used only moles to calculate K sub C, as the volume of the flask cancels out.
All right, that is the Kc, the K of C at that temperature. Remember, this is your HI, which is your product. Of course, that is this coefficient, these two becomes the exponent, and that is how this one becomes exponent in that case. But this one they both have coefficient of 1, so you don't have any exponent in this case. All right.
In general, it is a good practice to express concentration as molarity M. Example, a 2.0 liter flask contains 4.0 moles H2S, 0.80 moles H2, and 1.60 moles S2 in equilibrium at a particular temperature. Calculate K sub C at this temperature for the reaction. Write the expression for the equilibrium constant.
All right, I expect you to get your pencil and paper to write the expressions in this case. Everybody should be able to do this now, using the previous examples we've done. You get something like that, and then you look for your molarity. You are given 2 liters of flask, 4 moles of H2S, 0.8 moles of hydrogen, and 1.6 mole of S2. You get your molarity. Remember, molarity is moles over volume in liters. And that will give you that solution. When you plug in these values in there,
31.
you will get 31. All right, this section we want to look at the relationship between the Kp and Kc. We're going to see how they are related in one way or the other using this example.
The expression for K sub C is K sub C is equal to the concentration of HF to the second power divided by the concentration of H2 times the concentration of F2. And the expression for K sub P is K sub P is equal to the partial pressure of HF to the second power divided by the partial pressure of H2 times the partial pressure of F2.
All right, remember that I said for concentration, you have to use your brackets, but for partial pressure, which is the K of P, you are allowed to use a parenthesis. So the difference is just the sign, not the expression. The expression are the same, but the signs, the denotation are different because you denote the concentration with the bracket, and you can use parentheses for partial pressure.
Recall, for an ideal gas, PV is equal to nRT, or P is equal to N divided by V times RT. N divided by V is equal to molarity M, i.e. the concentration. Let N divided by V equal C, the concentration. Then P is equal to CRT. Apply this relationship to the K sub P expression.
All right, let's look at it once again. You have N over V, which is your molarity or concentration. So what we're doing is just replacing this C, concentration, with N over V. Remember in the previous pages, previous examples, that was what you used to find the molarity, because you are given volume and you are given the moles. So you just use the formula to find the molarity. And that's how this C comes about. So P equals to CRT. It's just like P equals to NVRT. So that N over V stands for the concentration, which is moles over volume.
K sub P is equal to the concentration of HF times RT to the power 2, divided by the concentration of H2 times RT times the concentration of F2 times RT. This rearranges to K sub P is equal to the concentration of HF to the power 2 times RT to the power 2 divided by the concentration of H2 times the concentration of F2 times RT to the power 2.
Now, remember that your RT is this. The concentration is this. So if your concentration stands for this, that means your RT will also be multiplied with that. We're talking about now a partial pressure for that. So the same thing applies to the denominators, which is at the bottom. You multiply it through by RT. But mind you, the RT is going to cancel out later on because you have RT at the top, RT at the bottom. So they're going to cancel out. Because this is RT square, and then RT times RT is also RT square. So they're going to be cancelled out. That is why you have your K of P equals to C of HF square over C of H2 times C of F2, which is, that means your K of P is the same thing here like the previous concentration.
Thus, K sub P is equal to the concentration of HF to the power 2 divided by the concentration of H2 times the concentration of F2. However, the concentration of HF, concentration of H2, and concentration of F2 are written as, respectively. That is to say, K sub P is equal to the concentration of HF to the power 2 divided by the concentration of H2 times the concentration of F2 is equal to K sub C. For this reaction, K sub P is equal to K sub C. For the general reaction, K sub P is equal to K sub C times the quantity RT to the power delta N.
So this is very crucial for you to memorize this. K of P equals to K of C times RT to the power of change of N. We're going to know how to get your N in the later on. Now, all this J, K, L, M stands for your coefficient. Remember that we talked about that in the classroom. They are all coefficients after you have balanced the equation. Okay?
Delta N is equal to the sum of the coefficients of the gaseous products minus the sum of the coefficients of the gaseous reactants. Therefore, for the general reaction, delta N is equal to the quantity L plus M minus the quantity J.
Okay, very interesting now. How to get your N, the delta N, change of N. It's just like the product minus reactant. You know, we're doing product over reactant for the expression. But in this case, you are going to have some of the coefficients of the gaseous products. Of course, L and M are the coefficients of the gaseous products, minus the coefficients, some of the coefficients of the gaseous reactant. So that means minus J plus K. So when you look at the coefficient, you add them together and then you subtract. That will give you your N. So your N becomes an exponent in this equation. Remember this equation very well. You may likely come across this in your exam. Take note of it. I don't think it's in the formula sheet. But you know, this is going to be online, so you're free to have all the formulas written by your side. It's an open book exam. Okay?
R is the gas constant, is equal to 0.0821 liter atmospheres per mole per Kelvin, and T is equal to absolute temperature. Example, for the reaction at temperature T, K sub P is equal to K sub C times the quantity RT to the power.
All right. I want you to look at this problem. What is your value of n here? What is your delta n? That is very crucial. What is your delta n? In this case, when you look at delta n, you know the product, which is 2, the coefficient of product 2 minus sum of the reactant. Reactant is 2 plus 1, right? That means you have 2 minus 3, which is equals to negative 1. By its products minus reactant. All right?
Delta n is equal to minus 1. Thus, K sub P is equal to K sub C times the quantity RT to the power negative 1. This equation can also be written as K sub P is equal to K sub C divided by RT, or K sub C is equal to K sub P times RT.
Remember when you have an exponent negative 1, it's going to be, if you have exponent negative 1, that means it's going to be the reciprocal of that. So in other words, what you have here is going to be RT will be at the bottom, the denominator. That is what it means when you have negative 1. It's going to be a fraction 1 over RT. That is how you got this from. And when you cross multiply Kp times RT, you get this. And then your Kc, that means your Kc will be that. So Kc will be Kp times RT. That is how this was arrived at. All right?
Example, consider the following equilibrium at 92 degrees C. Calculate K sub C for this equilibrium reaction. K sub P is equal to K sub C times the quantity RT to the power delta N. Delta N equals 2 minus 1 equals 1. Thus, for this equilibrium reaction, K sub C is equal to K sub P divided by RT. Thus, K sub C is equal to,
now, excuse me. Let me point out here. Remember, when you are calculating temperature in gas law, you have to be in Kelvin. So always remember to add your 273 to your degrees Celsius. All right? Because this case, you are looking for temperature, and you need to calculate it in Kelvin. Add 273 to the degree in Celsius to get your Kelvin.
0.0440.
All right, any question at this point? I guess everything is okay. All right, let's have an example.
A. Write the general relationship between K sub P and K sub C.
All right, get your pencil. Write your relationship. Remember your delta n, that is change of n, is going to be products, sum of the products coefficient minus sum of the reactant coefficients. All right, this will give you that. That is the expression. They say write the general expression between K of P and K of C. So you're just writing between Kp and Kc. So Kp equals to Kc RT exponent n. So what is your n? Remember it is 1 plus 3 making 4. That is 4 minus 2. That will give you 2. So this should be 2. So what will be your K of P?
Example, at 125 degrees C,
So that means 2 will be here, right? So this will be your expression for K of P.
example, at 125 degrees C, K sub C is equal to 2.6 times 10 to the power negative 5 for the following reaction. Calculate K sub P at this temperature. K sub P is equal to K sub C times the quantity RT to the power delta N. Delta N is equal to,
All right, what's your delta N? Delta N is 2. What is your R? Remember your R is a constant, so you don't have to memorize that. You get the value of 0.821. Your temperature, in this case, you have 125 degrees. So remember you have to add 273 to that to get your value. And that would be 298. So your K of P, when you solve this problem, you should get,
example, consider the following equilibria at a given temperature. A. For which of these equilibria does K sub P equal K sub C?
right, look at the 3 examples. Which of them will have equal values, like equal coefficient? That is what it's trying to ask you. Because coefficients will determine your equality on both sides.
B. Write the relationship between K sub P and K sub C for the first equilibrium.
All right, go ahead, write the equilibrium expression for that. Remember, this is your N. All right, you should get something like this. Remember, you are writing for between Kp and Kc for the second expression. So that means 1 plus 1 is 2. 2 minus 1 is 1. So your exponent here, which is your change of N, is going to be 1. And Kp equals to Kc RT. All right, the difference is just going to be the exponent.
Consider the general gas phase reaction. K sub C is equal to concentration of C to the power L times concentration of D to the power M divided by concentration of A to the power J times concentration of B to the power K. K sub P is equal to partial pressure of C to the power L times partial pressure of D to the power M divided by partial pressure of A to the power J times partial pressure of B to the power K. For a given system at a particular temperature, the values of K sub C and K sub P are fixed. When the reactants and products for a given reaction are mixed, it is useful to know whether the reaction system is at equilibrium. If the system is not at equilibrium, then it is useful to know the direction in which the reaction must proceed for the system to reach equilibrium. The reaction will occur in the direction favoring either the reactants or the products.
Now, does that make sense? Let's read it slowly and try to digest it. Because we're going to arrive at certain numbers when the equilibrium, of course, if you look at the topic here, it says the reaction quotient. Quotient means what? Quotient means answer. The quotient of the problem is the answer to the problem. So if your answer is less than 1, equals to 1, greater than 1, there is a reason for that. And that's what we're going to learn now. All right?
To determine the direction in which a reaction proceeds, one needs to determine the reaction quotient, Q. Q can be expressed as Q sub C or Q sub P, in the same way as we expressed K as K sub C or K sub P. For the general gas phase reaction, Q sub C is equal to the initial concentration of C to the power L times the initial concentration of D to the power M, divided by the initial concentration of A to the power J times the initial concentration of B to the power K. And Q sub P is equal to initial partial pressure of C to the power L times initial partial pressure of D to the power M, divided by initial partial pressure of A to the power J times initial partial pressure of B to the power K. Recall that brackets with the subscript 0 is defined as an initial concentration, and brackets with P subscript 0 as an initial partial pressure. By comparing the numerical value of Q, Q sub C or Q sub P, with K, K sub C or K sub P, it is possible to decide the direction in which the reaction will proceed to achieve equilibrium. Case 1. If Q sub C is less than K sub C, or Q sub P is less than K sub P, if Q is less than K, then there is more reactant and less product in the initial conditions than at equilibrium. Thus, the reaction will proceed towards the product side, i.e. to the right, such that Q increases and eventually becomes equal to K.
Any question on that expression? When your Q of C is less than Q of C, Q of C less than K of C, or QP is less than KP. Remember, this is KC and this is QC. So the two are not the same. One is when it's equilibrium, the other one is when equilibrium has not been attained. This one is at equilibrium, this one is when the equilibrium is not yet attained. All right? So if your Q is less than K, that means if the values you got from here, the coefficient, the reaction quotient is less than equilibrium constant, then the reaction will proceed towards the product side. That means the reaction will shift to your right, just like your product, just like we did in the Charlier's principle. All right?
Case 2. If Q sub C is greater than K sub C, or Q sub P is greater than K sub P, if Q is greater than K, then there is less reactant and more product in the initial conditions than at equilibrium. Thus, the reaction will proceed towards the reactant side, i.e. to the left, such that Q decreases and eventually becomes equal to K. Note, if Q is equal to K, then the reaction system is already at equilibrium under initial conditions, and there is no change.
All right? Any
Example, for the synthesis of ammonia at 300 degrees Celsius, predict the direction in which the reaction will proceed to reach equilibrium when the initial concentrations of NH3 and Cl2 and H2 are 0.001 molar, 0.0001 molar, and 0.002 molar, respectively. First, calculate Q sub C. Q sub C is equal to initial concentration of NH3 to the power 2 divided by initial concentration of N2 times initial concentration of H2 to the power 3. Initial concentration of NH3 is equal to 0.001 molar. Initial concentration of N2 is equal to 0.0001 molar. Initial concentration of H2 is equal to 0.002 molar. Q sub C is equal to 1.25 times 10 to the power 6. K sub C is equal to 5.2 times 10 to the negative 2. Thus, Q sub C is greater than K sub C.
So in this case, what happens? Where will the equilibrium shift to? When the K of C is greater than K of C.
Q is greater than K. Hence, there is more product and less reactant in the initial conditions than at equilibrium. Thus, the reaction will proceed to the reactant side, i.e. to the left.
All right, any question on the applications now? You can see how the question can come. They will give you K of C, then you have to find the Q of C. Then you compare the two to tell them which direction will your equilibrium shift to. Is it to the right or to the left? Is it to the product or to the reactant? All right? Right, let's do some interaction now.
The reaction system at 298 Kelvin. Predict the direction in which the system will shift to reach equilibrium when 1.0 mole of HOCl, 0.10 mole of Cl2O, and 0.10 mole of H2O are placed in a 1.0 liter flask. First, calculate Q.
Right, calculate the
The
QC.
expression of Q sub C for this reaction is.
So I want you to complete this assignment. I want us to stop here, and I will give you some other problems at the end of this for you to practice and send it to my email. All right, so what you have to do is to solve that problem, and then we continue from where we stopped today for everybody, so that I don't want to give you too much today. So please go over the video once again. If you have problem with any section, send me an email so that we can talk more on that. All right, thank you.